So this is the second part of the entropy concept and lecture. So we're going to continue on with our discussions and talk a little bit about thermal equilibrium. So just like how we said before about how if we have these two systems that are in thermal contact, that energy is going to transfer between them. So what we can do is we can take the same concept that we had before and just relate it back to energy. So once again, if we replace the half spin excess with the idea of energy, what we end up getting is this: the total number of accessible states is the sum of all the products between these accessible states. And then we could define the most probable configuration with, I couldn't really put hats over these U's, but you get the idea of the most probable max U1 and U2. Now we find the min and max pretty much the same way that we did last time, where we take the derivative here. This time we're not going to use the Gaussian equation since it doesn't really apply here. Instead, though, what we get is this, that if we take the partial derivative of this with respect to u1, and then we have this, and then we take the partial of this with respect to u2, um, and that's where this equation's coming from. So again, this is some calculus stuff that you want to kind of remember, that when you try to take a derivative of something like this that has multiple variables, you have to do a sum of the partial derivatives. Uh, and then we once again set this equal to 0 in order to find the min and max values. So what this tells us is that we know that du1 plus du2 has to be equal to 0. That if one changes by some amount, the other is going to change by an equal amount in the other direction. That if this goes up by, let's say, if this is 1, this is -1, so it always equals 0. All right? That's like that the whole idea of conservation of energy. So when we combine that idea that the changes in du and d2, u1 and u2 are the same with our most probable configuration equation, well, we can drop them out, and then when we put all the system 1 values and system 2 values on the two sides, we end up getting this equation. We can further simplify this. Now, this is a very common trick that you're going to see me pull many times in this class. But what we can do is we can actually combine the the delta G1 over G1 with delta ln G1. As you recall, when you take the derivative of a log function like this, it's just, you know, it's the derivative of whatever's inside divided by whatever's inside. So we can almost kind of reverse that into this partial of the ln function. From here, we can actually then simplify it one step further by now bringing in the concept of entropy. So we're actually going to define the term entropy as an equation, at least, as being defined as ln of this multiplicity function. So this is our entropy equation, that when we know the number of accessible states and we take the ln of it, that's what the entropy is. So what we end up getting is that for thermal equilibrium to occur, this is going to be true, that the partial of the entropy of one state with respect to the energy has to be equal to the partial of the entropy of the second system with respect to the energy there. And then these symbols here are just saying that the number of molecules in both systems are remaining the same. I just wanted to go back to this equation. You may notice things like this where there's 3 lines. If you didn't know this already, that's usually used for something as a definition like this, where the term entropy is being defined by this relationship rather than saying that, oh, this happens to equal to this. So it's more of like a more concrete statement that's saying this is always true because it's a definition rather than, a happenstance equation that may occur in one type of scenario. All right. Now, one thing to note is that the entropy of a system is going to be an additive property. That if we want the total entropy, it's going to be the sum of the entropies rather than the products. Now, at first, this may seem like it doesn't make sense, but if we go back to the definition of entropy, I think I showed here. Yeah, so the definition is ln of g. Well, g, the total number of accessible states, as we said before, is a product of the two systems' multiplicity functions. So uh, our entropy turns into this. Now I can use the ln functions and the identities of them to separate them as ln of g1 plus ln of g2, because that's what happens when you have two things multiplied inside of a log function. And then that goes and turns into here. So this is the proof that states, oh, we can actually turn this into an additive property rather than a multiplicative property. Another thing that we know is that when the system ends up reaching this thermal equilibrium, as the namesake implies, their temperatures are going to be the same. So what we're going to have is this equation. Um, this equation pretty much comes, I can't think of exactly where it's coming from, but it's another equation that we had from the thermodynamics section that relates the change in entropy being equal to this stuff, the 1 over T being equal to KB, where KB is defined as the Boltzmann constant and is given this specific value. Now, one thing that I want to know is you're going to see, I believe, a little bit later on, maybe in this lecture or maybe in a future one, that there is a slight difference between this symbol of entropy and the symbol that you might see in some other classes with that has the capital S. Um, the only real difference is this Boltzmann constant. That's really the only difference between this entropy symbol of sigma and the entropy symbol that you would normally see in like chemistry. All right. So because of the fact that the KB, the Boltzmann constant times the temperature comes up so much, a lot of times what they do is, well, we're going to simplify it and talk about something called the fundamental temperature being represented by tau. And that's just, again, being defined as KB times T. So it turns our equation into this. So one thing to note is that this tau is actually measured in energy, in the units of energy of joules. Now, this actually allows us to make a much stronger case between the concept. If you remember in the thermal class, that we mentioned, or that you should have learned, that temperature is considered the average kinetic energy of the molecules. Now, for me, I remember it didn't really always make sense that we called this the average kinetic energy when the units don't even make sense with energy. Well, now that we have this concept of fundamental temperature, it will actually make it more aligned and make more sense with that idea of temperature being average kinetic energy, if we relate this as being the true temperature and this just being a almost a scaled version of the temperature. All right, so we started off bringing up the definition through a mathematical point of view of what entropy is, but now when we want to actually go more conceptual of what is it, the entropy is being defined as the log of the number of accessible states. Now, what this really means is it's giving us a number towards how many states are available. You've probably heard the phrase of entropy being the amount of chaos or the amount of disorder in the system. It's relating to this idea. Think back to what we said about the whole the number of possible states for different half spin systems. The idea that some of them have more possible combinations than others. So, for example, in a four particle system, there's only one state that has all four particles pointed in the same direction. But there is, I believe, I want to say six combinations for having two particles pointed up and two particles pointed down. Forgive me if that number is wrong. Doing it in my head, and I'm just trying to remember off the top of my head. But the fact that one system has six different possible combinations, while another state has only one possible combination, that's the disorder that we're talking about. That if we're in the setup of, oh, we know that two of the spins are pointed up, well, technically that's, that could be one of multiple different scenarios. But if you have a case like we know that all four are pointed up, that would have a lower entropy because, well, we actually do have a much better idea of which combination we're talking about. So this goes back to what I said before, that sometimes you might see entropy represented as a capital S. Like I said, this is from other classes. This is just basically getting rid of that KB term and bringing the Boltzmann constant into with the entropy. So this is an equation that you can use to go between the entropy represented by S and the entropy represented by the sigma. And then this is probably something that you've seen in other classes. In particular, like I said, if you've taken a chemistry class, that entropy is KBlNG. So that's pretty much where it's coming from. A lot of times this is called conventional entropy. It doesn't really matter. And that's pretty much it. This kind of says the same thing that I said before about how when we mention that something has high entropy or high chaos, it really means that there's more possible states available for a given setup, for a given macro state, like, four particles pointed upwards versus two up and two down. All right, so here's possible. Here's a question that you could work on. Pause the video, work on the stuff, and we'll go over in a second. All right, so here's a practice entropy that we can use. So we want to figure out what the entropy of the system is. Now, in order to figure out the entropy, we need to know the number of possible states available. So what we have is, we know that there's 50 chairs and we know there are 13 people inside of this. So at most 13 seats could be occupied, and then the other 37 are unoccupied. So I need to figure out the total possible states using the factorials. Again, we're using this because of the small numbers. And we end up getting that the total available combinations in this setup is given by this, a fairly large number, 3 times 10 to the 11th. So the entropy of this system is just taking the ln of this, which gets us 26.6. Now, for the most part, what you'll see later on, and what you've probably heard before, is that the concept of entropy by itself is not really useful. It's not super important of knowing, oh, the entropy is 26.6. It doesn't really mean anything. What's more important is how the entropy changes, how the entropy goes from one point to another. Is it increasing? Is it decreasing? And if so, by how much? Usually that's how entropy is going to be used in this class and in most thermal dynamic classes. Pretty much similar to potential energy, where you always want to have a reference point so that you can talk not about the total potential, but how much that potential is changing between 2 points. All right, here's another question you could work on. Pause the video, work on this stuff, and we'll go over it in a second. All right, so going back to the 52 cards being shuffled randomly, we want to know the possible arrangement. So once again, we're going to figure out the multiplicity function. Now here we're not actually pulling any cards out, so what we can do is just say that the total possibilities is just 52 factorial. The fact that the first card has 52 uh, different things that it could turn into. Once we define the first card, the second card is going to be one less possible possibilities. The third one's two less, so on, so on. This just becomes a 52 factorial. So there are this number of arrangements. Now, this leads back, if you continue on with some of this stuff, you've probably heard the statement that there's never been a case where, or mathematically, it's pretty much impossible that if you shuffle a deck, that you're ever going to get the exact same. Well, if you do a perfect shuffle, that it's impossible to do get the same exact combination every single time as someone else. It's because of the fact of the supremely large number of arrangements possible within a 52 card deck. To find the entropy, we just take the ln of this and we get 156. All right. So, like I said, we're going to talk a little bit about change in entropy. So, we're going to look at how the entropy changes when the system's coming to a thermal equilibrium. So, we can find the change by going back to the definition of entropy and saying, well, it's we can set it equal to this, that it's going to be the amount that the one entropy changes plus the amount that the other one changes. And then we add in these partial derivatives. If you don't see where this is coming from, just the way I always thought about it is that just like how you can multiply a fraction, multiply something by 4/4 in order to balance out the denominators, we're pretty much doing the same thing here. Multiply this by delta u over delta u, and then just moving one of the deltas under here. From our definition of entropy being equal to 1 over tau, that gets pulled into here. So we end up getting this, the delta u's being the same for both. And then what we can see is that when tau 1 is greater than tau 2, which I believe was one of the definitions that we stated, that the entropy change will always end up being positive. Once again, this is something that we've covered before in other classes. So here's a question. Pause the video, work on this stuff, and we'll go over it in a second. All right, so what we're going to do here is we're trying to figure out the amount of energy being transferred between the two systems. And then it's coming to some final temperature. So they tell us the specific heat and they tell us the range of temperatures that it's going to, that it makes sense for this specific heat. So in order to actually do this, we have to go back to basic thermodynamics with the whole MC delta T equation. And we end up getting this, that the change in entropy for both is going to be the same. So we end up getting MC delta T for both because of the fact that both items, both systems, are identical with the exception of their temperatures being different. That means that the MCs on both sides can be dropped, and then we're left with this, that essentially the change in temperature of one system is going to be equal to the change in temperature of the other system. So this makes it very easy for us to figure out what the final temperature is going to be. We put that in, and we get the 320 Kelvin. One thing to note, you may notice that it's not always here I have final minus initial, but here I have initial minus final. That's mainly because I dropped this negative that was over here, and that negative actually moves the final on the other side. Another way of thinking about it is that the change in temperature should always be a positive number. So because here the final temperature is going to be higher, it's in front of here, but over here it's going to be lower, so we put it at the end. That's pretty much it. That it's always kind of absolute value of that. But once we get that the final temperature is 320, we could go back to our equation for the change in energy and figure out that for system 1, it's going to end up losing 117 joules, which means system 2 is going to gain 117 joules. Here's the next part. You can pause the video, work on this yourself, and we'll go over it in a second. All right, so we want to know the change in entropy when the about zero point 0.1 joules is transferred. The way we're going to do that is by using this equation. So we know how much energy is being transferred, and we know what the temperature is of the two setups. I'm not really going to figure out what the new temperature is for them. I don't need to do that. I can actually go back to using their original temperatures. The reason why is because of the fact that they made the temperature here, sorry, the energy change so small that they're pretty much trying to hint that the temperature didn't change. If you want, you can actually test this. Use the MC delta T equation, see how much energy or what the new temperature would be, and you'll see that it's barely noticeable. So from here, when we plug our numbers in, making sure that we bring in this Boltzmann constant relating the fundamental temperature to the absolute temperature. And we get that the change in entropy is equal to this. So the entropy does immediately go up, though it is a small increase. It is definitely increasing, something that we know is true for any closed system. Okay, so the this leads into one of the things that we know about entropy, and that's the fact that entropy is always going to end up increasing. That the only times entropy doesn't increase, there are two cases. One, if we're dealing with an ideal system, so an ideal reversible process. So a case like one of those ideal engines that continually goes from one state to another and then back to that original state. In those cases, entropy does not change. But again, those are ideal reversible processes which don't occur in real life. The second case, the only time entropy will end up decreasing is if we're not considering the entire system. So, for example, if we look at a piece of ice freezing, that has the entropy decreasing. It is going from a state of large number of combinations to a state where it has less combinations. It's more organized, less chaos, however you want to say it. But the thing to note is that the only reason why why water would freeze is because heat's being transferred somewhere else that we're not taking into account. So while that entropy is decreasing, there is a place, the environment eventually, that is increasing the entropy even more. So the main thing though is in any real process, when we consider all the available systems, the entropy will always end up increasing. Now, this does make sense to what we've said before. Again, that's the whole point of what we're doing here is we're going to the microscopic level and kind of building everything from there rather than doing it top to bottom like you've done in other classes. So if we go back to the idea of what entropy is, well, the entropy is essentially related to the number of available states. And one of the things that we mentioned is that as a system goes to thermal equilibrium, the number of accessible states is always going to end up reaching a maximum value. So since the number of states reaches a maximum, that means that entropy will always have to end up increasing to a maximum. Now, here are a bunch of different ways that you can end up increasing entropy. You can add particles to the system. Again, going from two particles to 10 particles drastically increases your number of available states. Adding energy to the system changes the number of available states, increasing the volume. Decomposing the molecules kind of goes back to adding particles and energy to the system, and then letting polymers curl up. All these are different ways that you can increase entropy. Of course, we're not going to talk about all these. I don't think we're really going to talk about the polymer one. But again, a lot of this really goes back to the idea of going from one organized set of cases to having more available states. All right, so I'm gonna end the video here, and then we'll continue talking a little bit about some of the laws of thermodynamics. Again, using our concepts of the multiplicity function and available states in order to get some of the other equations that we've gotten in previous classes. If you have any questions, please feel free to let me know. Otherwise, I'll see you in the next video.